Hello again, I'm John Ball, and today I want to talk about artificial intelligence and what's going to be coming up in the next few years. Many people think that artificial intelligence is nearly solved, and as a result, all we need to do is compete for the spoils. Another approach is to say we haven't really started to get AI to work yet. And I'm of that view that we've certainly done a lot over the last 70 years, but the fundamental brain emulation hasn't yet been done. Why listen to me? Well, pattern brain theory is the first non-computational system that I know of that explains why we see brains doing what they do. And I've been able to use that technology to emulate it with linguistics. So it's a pretty strong case for the alternative to the brute force computational models that have been so popular over the last 70 or so years. But let's just move away from the White House announcement of Stargate, where in order to service the large needs of AI today, such as needing big data centers and power stations to drive them, potentially building nuclear power stations in order to drive these data centers, perhaps we can just have a look at what the options are between the deep learning models, so the large language models or generative AI that's around today, versus deep symbolics, which comes from the pattern brain theory, my brain theory, which is something that's low energy in use. And, you know, when you think of it, this thing in our heads is using something like the energy of a 12-watt light bulb compared with a data center that's driving modern AI, which might need gigawatts of power. So there's a valuable opportunity just to go through what these different technologies are. So let's get into it. I saw this article from MIT News yesterday, and it was talking about power-hungry data centers stressing grids. So it's a topical subject. And when you look at the detail, it's not just that they consume a lot of electricity. It's the fact that there's this increase in the usage of electricity. So by 2030, instead of 4% of the total energy in the United States being used for power for data centers, that fraction could rise to 9%. So it's a big increase. And is that a problem or not? Well, I think that's a great article. And by the way, all the articles I'm going to reference will be shown at the end of this talk. Okay, so let's have a quick analysis of deep learning or large language models, generative AI, the one that generates the next word. It's a prediction engine, a statistically based prediction engine, versus deep symbolics or a brain-like emulation of what's going on. So the first thing that happens with deep learning is you train a neural network. And one of the examples is that 45 terabytes of data, so gigabytes, it's a very large number of a very large amount of data is being put into these neural networks. So the analogy that was used, how much computation trains these things? And if you had 1 billion computations per second, that's more than 100 million years of work for that type of computer. And the thing that allows these machines to be operating today is GPUs and various other technologies that convert that into some sort of parallel processing scheme. But fundamentally, it's an incredibly computationally intensive approach, and it's then got some problems it's got to deal with. So anyway, we have a whole lot of computations that have to take place in order to produce one of these models. The neural network underpinning it, what it's doing is it's finding repetitively the next word in its prediction engine. So it takes all of this training information, and if some sort of input is provided to it, it then uses next word prediction repetitively to produce a response. And the problem with that is if you're simply doing next word prediction and you want to understand what was said, you can't. You're just getting a response. The system is set up to give you a response. And then if you want to understand what was going on, you would have to produce another system or somehow drill into data to work out what's going on. So it's not built for interacting with people, which most of these systems, the best use cases are where they're solving problems for users, but it doesn't fit in with generative AI. So the process, when you look at the details, it's similar to the training run in the first place. It's very numerically intensive. An awful lot of work is going into this prediction engine, and it's therefore quite expensive. So once the applications are created in this generative AI world, then fine-tuning takes place, because the generative AI produces errors, and something has to be done to make sure, if you were a corporation using it, you wouldn't just be making up lies for your customers to see. So fine-tuning is one technique that gets used. RAG, there's a whole bunch of techniques where people can take the output of a large language model and try and get it to work correctly. In my theory, what you would do is simply get your basic scientific model to work, and then use the engineering to simply pull out the correct answers. So we've got a different approach to engineering, but this is the world. Maybe the engineering approach is going to win. So the issues here are that there's applications to write. The system doesn't just work. And then if you want to integrate it with a corporate environment, you might have to have somebody writing SQL to query databases and pull information out of legacy systems. And potentially it's quite a big task. If we now look at the deep symbolics, the alternative to that, well, we start with dictionaries and phrases. So if you do the analysis of what makes the language work, as a child, you learn the basic words that make that language operate. And as our brains are learning what those basic words are and how they interrelate with the rest of our brain, we're then in a position where we can get by in the language. We just keep learning vocabulary. And if we emulate that model, that's going to be much more effective, because the base language plus various amounts of knowledge is going to then replicate what the large language model does, but much more cheaply, because it doesn't have to do it repetitively. So in the dictionary, what we need is word and phrase coverage for the use case. And experience shows, as we went through English and 8 other languages, that a very small core of phrases is needed in order to represent the entire language, because we very much use phrases and then reuse them. So there's a lot of reuse of patterns in a brain. The next thing is storing context. So this is the knowledge for language. And it's the knowledge that we have. It's basically language independent, but when somebody talks to you, you convert that language into meaning, and that meaning is part of your knowledge base on the things that you're talking about. And amazingly, there's been some excellent work over the last 70 years on how to represent knowledge, or what the things are that brains do in order to use knowledge. So in this case, in the deep symbolics model, there's an application focus. So if you've got an application that's, for example, taking people's names and addresses and then providing a product of which you've only got a couple of products, you can imagine that all of those types of dialogues aren't that complicated. In fact, let me just revert back to here for a moment. So as we, the application focus here, if you were to store the knowledge required to sell one of 3 products that have a bunch of features, there's not a lot of knowledge there. The large language models are scraping the entire internet and all these documents for building a combination knowledge base and language base, but you don't need to have that. You can just have a small amount of knowledge that's providing enough for the purpose of your system. So it doesn't have to be intensive, because it's basically built on language separated from knowledge. And by using those 2 things independently, you only need what's required for your application. Maybe you need a couple of languages, but the same knowledge, for example. Okay, so if once you create an application, the language is tested as part of the entering of the language, because there's a lot that we know about how language glues together. So if you're running, for example, if an animal's running, we know that we know what running means. If a candle is running, we know what running means in that case. So there's a combination of the meanings of words, ensuring that it's understood in the context of your dialogue. So if you assume that the language is tested, then what you focus on is getting the right context, the right knowledge so that you can answer your customers' questions. And you want access to legacy systems. So if you wanted to pull, for example, their bank details, you could simply do that and then present it in a natural language way. So this focuses on the legacy application, not on getting language to work or the other things that take place in the other world. Okay. So what's the problem? What's the thing that's generating the need for new power stations, new data centers, new GPU hardware, and basically a race to try and produce these very expensive environments in order to train, retrain, and operate these statistical systems that are based on neural networks, artificial neural networks? Well, in the case of deep learning, there's massive data to produce the possible phrases. So if you write something, it's going into its trained database to see and find, have I seen a phrase like that before? And if it has, then you've got like a knowledge base, a sequence that you can rely on as being grammatical and having some sort of meaning with a system that's used for word vector meaning. And there's the problem. They're tightly coupling knowledge with language. So the weakness here is that the knowledge base is a statistical knowledge base, so you can't rely on the fact that the generation is what was ever said, and that leads to fixes that we'll look at in a little bit. The next, word prediction can hallucinate. So that's the problem, where the generator is simply going through and statistically generating a next word, which is grammatically valid. It sounds like, for whatever language it's generating, it sounds like the right type of thing because that's how it's built, but it's not true. So that hallucination creates trust problems, and the ecosystem that's developing around these large language models is looking at how it can remove those errors that are being generated frequently from the large language model. So the word vectors are at the core of this problem. So nobody ever said that a number represents language. What the numbers are doing in these word vectors in the large language model scheme is it's simply creating the ability to do similarities. So if something's read and something else is read that is similar, even though it's not the same words, it can still store the representation of those words nearby each other. But it limits accuracy. And subsystems are built to deal with those limitations. So errors like hallucinations, let me just move my head again. So hallucinations can need to be protected from users, and the applications are then focused on how can we validate with all of this stuff that's being generated and without a good way of testing it, how can we make sure it's all correct? And that's just an ongoing engineering problem to fix that. On the deep symbolic side, what we're doing is we're creating a dictionary once per language. So English would have a dictionary, French would have a dictionary, Portuguese, Romanian. Each language that's significantly different has its own vocabulary and phrases. And the reason will become a bit more evident when I show you how these systems work. But basically, if you spend the money to produce a dictionary, they're never trivial tasks because there's potentially hundreds of thousands of words in a language, but I'll get back to that in a moment. If you have a representation of a language and that simply converts words into their meaning, what's left to do for the next 30, 50 years? Because languages don't change that rapidly. You can always update words into a dictionary and it'll keep working. The system will keep working because the system's working off the meaning of the words, not off the words themselves. The interesting part when we investigate more about how languages work is really it only takes maybe the first 100 words are used 50% of the time for a typical language. That's 50% of the words in use are simply gluing together the different concepts that we're using, words like and but, the, a. So they're providing useful information that we use to understand the context of what's being said. with only the first 100 words, we can then understand a lot of what's being written sort of as a framework. If you get up to about 4,000 words, you're covering 95% of most everyday applications of that language. So the point is that once you understand that language isn't that complicated, it's not got that many words, you then say, well, what's the rest of the words? Well, guess what? There's an awful lot of human names in the world. There's streets, countries, company names. And all of those will reuse some of the words that they combine, or acronyms, but in order to understand a language, you don't need to know everything. You only need to know the types of things that people are talking to you about. So the addition to the language then is the knowledge. So what knowledge is required in order to build a system? And the types of information when you call, for example, a help desk, one of the things they care about is who you are. If you can identify who you are and then what products of theirs they've got, they're in a much better position to help you. And it would be possible in this new world model for the user to share their lossless representation of knowledge in such a way that call centers could have access to it if you shared it with them, and things would continue on from there. So the data model basically pushes these big data models into the corporate area of control, and then they have to find from their data how you work with them. In the new world, we could simply work with the user keeping their own information and sharing it with people that they're working with. So it's an opportunity to make this much easier to get a good result for the consumers. And then the applications are only using the scope needed. So again, I'm just stressing the point that when you've got a large language model with a whole lot of trained data, or maybe fine tuning, or maybe other tricks to try and make it accurate, they've got to cover a wide range of things. But once you're focused on a very narrow use case, and you don't need a lot of knowledge, you just care about the language working. And so in this case, you'd be able to reuse pieces of applications across multiple enterprises. I'll give you an example. If you call a help desk, they usually ask you for your name, perhaps your address, maybe your phone number. All of that sort of information has a series of questions that would be asked in order for you to communicate that with a machine, with a robot or a bot. But it doesn't need to be a big task. So my point is that those types of interactions of what's your name and address could all be stored, optimized, and then shared across thousands or millions of enterprises that use that language without everybody having to build their own, because ultimately it's still providing the same data. All right, well, let's get into how all of this works and what the problems are. And this is Tom Dietrich, and I find his work excellent. He's one of the founders of the machine learning environment. He seems to know everything about it. I've sat through some of his online talks, because if you care about the deep learning model, which uses machine learning at its core, he seems to me to be the guy that's really talking through what the next steps should be, or what the problems are that need to be resolved. And this is just one frame from his critique of large language models and what will make them better. And you can see here, we want knowledge bases, not statistical models of knowledge bases. And so the making up of responses comes from the fact that there's not a built-in knowledge base. Thanks, Tom. Another guy that I found excellent at explaining large language models is this guy, Grant Sanderson. He was presenting, I think it was an hour-long presentation in this video, 57 minutes. And what he's showing here is how the word vectors are being manipulated in a large language model in order to retain the meaning of more complex phrases. So, for example, here we've got a fluffy blue creature where he's got a representation of the creature being this cute little round thing, blue being this color, and fluffy being this texture. And automatically, based on the large language model's training and the prediction, if you do enough prediction with these vectors, because that's the underlying vector representation, you're going to get that combination allowing you to have this image representation or the word can mean all of those 4 vectors added together. And similarly, the verdant forest could be represented this way as a forest plus a color. And in terms of the vector itself, it's just a number, but that number in vector space, when you add and subtract these other elements, gives you a unique position in vector space that can then be used as a differential against other types of representations. Again, the large language models are focused on the vector space, and that's so that they can do a similarity or a comparison between this unit in vector space and that. And if they're very similar, then you can do one thing, and if they're quite different, you can do something else. So all of these vectors, when you look at Sanderson's explanation of what the sequences are, you go, wow, that's an awful lot of processing going on. And maybe we don't need to do that, and we don't. Okay, so when it's recognizing in its training set, the large language model, the fluffy blue creature around the verdant forest, the first thing it's doing is predicting what the next word's going to be and training in order to accept fluffy, and then to accept blue as the next one, and then to accept creature as the next one. So it's constantly predicting. You think, well, okay, well, that's not a big deal. It can predict. But in this other example here, you can see the scale of the computations that go on in order to do each one of these comparisons to do the prediction. So we've got some information here, and there's a bunch of extensions to the word vectors, which could be, I don't know, a couple of thousand numbers. Maybe it's 100 numbers. It depends on the designer. But then it goes through this query, key, and value interaction in order to work out statistically how do these two words relate to these other words, and therefore how can we then do the prediction at the end. You'll see how it's done in a symbolic model later on. But there's a whole lot of statistics going on here, and in this particular example that I give in the at the end of this presentation, you'll be able to watch each of these videos and see the full detail of what's going on. My point would be that there's a whole lot of work going on, and if you didn't use word vectors, which this whole system produces confabulations or makes things up at the end of the day, rather than going through all of this effort, if only we had a system that would work and do most of this, we would be able to build, instead of on these machines that need supercomputers to drive them, we could build them, like my system, where it runs on a laptop, and it's got everything that it needs, that we could simply send a couple of files around and people are up and running with applications. So let's keep going. So here is an example of what comes out of a semantic network or a context network. So here, when people talk to each other, one of the things we build is this concept of context of utterance. So when you're talking to someone in a conversation, you don't have the entire world's knowledge that you're assuming. What you're assuming is what you've talked about in that conversation. There's it's part of the pragmatic side of linguistics, discourse pragmatics, where when people are talking to each other, they store things in active and accessible, and there's a science behind it. And so the context, there's certain rules that you follow. So inside the context of utterance, you would know that the people in a particular situation, if I'm talking about my one of my online articles, in Researchers One, called How Brains Work, not a particularly clever title, I suppose. I'm the writer, and so this information, I know that only readers of that particular article would have had a chance to have ever heard of it. We know its location, and all of this is knowledge that then applies to the rest of the conversation. And so when we look at John Ball, if we go to John and we know that he did some work and it took place on the internet, these layers are a possible way of representing all of that with just a couple of associations. And if you know that John is a man, and that a man is a person, and that a person is an animal, and that animals move and have multiple cells, and people have 2 eyes, 1 head, 1 nose. Or perhaps that's inherited from a certain type of animal that doesn't happen to be in this particular environment. Well, generalization of context is possible. So the generalization comes from the fact that by storing information based on its meaning and having all of these associations that you have to have in order to understand the meaning, generalization simply falls out of this model. And so by simply automating the creation of this central knowledge repository, which we've done it with dictionaries and encyclopedias with a somewhat random approach, we could do it with a very methodical approach and then make it accessible to all users. Anyway, the point is that with just a couple of associations, if you were to say, does John move, we could simply scan down these links and go, yeah, John does move because John is a man who's a person who's an animal and moves. And the system which I built uses these types of tricks as a great way of doing generalization. Okay, so I showed you a quick introduction to how large language models work. Let me give you a quick introduction to how deep symbolics works using pattern brain theory. So here, what I'm showing, and it's probably a bit small for you to see, but these circles represent the different types of information that take place when we speak a language. So, oops. So if I don't hit the mouse button. So you start with sound that we've got the sound that people can make across the world's languages that are a little bit more refined when we get to particular languages. And then you go from that to words. We resolve the pragmatic. So what does that word mean in context? So if I say I, you, or he, she, the I is referring to the speaker. So if I say it, it's referring to me. If you say it, it's referring to you. And we, in order to store language in a lossless manner or its meaning, we want to resolve those things on the fly. So we do some context resolution. We work out the syntax. How do these words fit together? So those are phrases. And then we do the semantics, which is what does this phrase mean? And often we bundle multiple phrases inside each other in language. So you finish up with an explosion of embeddings that you need to work out, well, is that embedding valid versus this and so forth. Just a quick aside. In 2016, Google released their Parsing McParseface. That was their name. It was a parser, a statistical parser. And what it would do is you'd put in a sentence and it would then break it down. And they pointed out in their press release for that tool they were making open source. In fact, it was called SyntaxNet, the system the more generic system. But when it was producing an output, it would have to sift through, for a 20-word sentence, sometimes 20,000 structures. So with the original parts of speech model that was popular in linguistics, probably till today, where you would look at the syntactic model of language with nouns, verbs, adjectives, adverbs, prepositions, all of that stuff is syntactically focused. And what it does is that syntactic model creates a combinatorial explosion of possibilities. The alternative is based on meaning, which is looking at the main meaning components, predicates and reference. Reference being things that are in the world, and predicates being things that relate other things. So that complex model of nouns, verbs, etc., created a combinatorial explosion. And Google was pointing out in that 2016 release of their software that 20,000 structures had to be sorted out from only 20 words in a sentence. So that's the challenge that has made natural language understanding so difficult. And because since the 1950s, since Chomsky's syntactic structures monograph was released, people have been focusing on how can we build these syntactic structures based on parts of speech. And guess what? It's been hard. The alternative based on the semantic pieces needs a little bit more work as well, and I'll explain that in a moment. And now I've just hit that back button. Okay. So these are the things that are built, and you can't solve them without solving them holistically. So the sound that you hear might have distortion in it, So the only way you can work out of the possible meanings of a sentence is you get right up to the context and you go, this makes sense, that doesn't make sense, I'm choosing this one. But most systems have been built looking to parse only at the syntax level, not even doing the disambiguation of the words until later. And so you've got a mess. You then have all of these syntactic structures to solve. But if you use semantics and you resolve things as you go, which we do in our systems, then you can resolve the phrases and therefore know, well, this phrase makes sense, that one doesn't. So I'm only going to look at combinations of this one. At the end, maybe you're listening to somebody speaking a foreign language and you can't work anything out, but there's your stack of challenges that you have to solve in order to understand another person's language. So another way of looking at it, what I just said, is in this diagram here, which is in my recent book from November 2024, How to Solve AI with Our Brain. And in that, you can see that basically you go from sounds to what those sounds could mean in your language, to then morphology, so putting together words or syllables, then working out syntax. And all of these arrows are showing the bidirectional nature. So this makes sense perhaps at the syntactic level, and then you pass it on to the meaning level and it goes, no, that doesn't make any sense. So here's the model of how language works. And if we look at it in practice, it's not too dissimilar from the large language model or the deep learning model. You start with these words. In the case of large language models, they're tokens. And in deep learning, that would connect to a word vector. In this system, it connects to a symbol, which in this case represents one or more meanings. And inside those meanings, you can then have those strings, which I showed you on the last screen. So a cat is a kind of feline, a kind of animal, kind of entity. And you can pull off things at whatever level is necessary to generalize that way. When you crawl, it's a type of movement. And so, again, you can use the syntax, for example, around move to make sense of very large numbers of predicates. Notice the P for predicate, R for referent. Doesn't really matter. There's an adverb, which, again, is a predicate. You can crawl slowly. So this is where you can resolve things on the fly really efficiently. So when the large language model is computing the next word, it's going through all of these vectors, trying to work out similarities and trying to narrow down what makes sense in this particular sentence. But here, because of the type of predicate crawl is, you can crawl slowly. If we said the cat is tall slowly, it wouldn't make any sense. So depending what this word is determines what types of other predicates can connect to it. So let's keep going. When we match a more complex sentence like the man saw a red car, the components here, we create a consolidation set. This is from a patent. I've covered this in detail. Why is that relevant? Well, because it's been well thought through and documented. So this is not something that's difficult to replicate. So if the man saw a red car, the man has its own meaning. So we create the consolidation set of syntax, and then we create the semantic set, which is the meaningful unit independent of language. And then when the man saw something that's syntax, a red car gets resolved in parallel. But here we've got the predicate red, which we add into a consolidation set. So here's some more syntax. A red car is syntactic. But then we work out what its meaning is. And in this case, the meaning of a red car is a car has a property of being red, not surprisingly. So that property of being red gets plugged into the man saw this thing, the car. And so now we get our representation, our semantic model, our meaning, which is something. The man sees something. What does he see? He sees a red car. What's the red car? Well, it means this. So all of it goes together like a computer program. You're simply selecting the right pieces that make sense. And the right sense stuff is covered by another linguistics area of expertise, the semantics. So semanticists have spent a lot of time analyzing how you work out what makes sense of all of the possible dictionary definitions. And we're applying it. It works really well. Okay, so then the last thing I'd show you is this. if you had input as the cat ate the rat continuously, slowly on the mat today, evidently because it was hungry, all of that plugs into, there's a bunch of things resolved first, but in syntax, it all has to fit into syntax at some point so that you can group it all together into its meaning. And then this here is like the semantic set for what you've recognized over here. And there's defined layers so that, the cat PSA is a privileged syntactic argument. It's sitting here at the core level because it's the cat eating the rat. And so that is representing its meaning. And then the other elements like the continuously that lives at one level versus time and space today on the mat, that wraps that event of the cat eating the rat by time and space. And then the reason that takes place because it was hungry sits on the outside. So all of that is really well defined in linguistics theory, in the role and reference grammar. And so that's the thing that you store into context. So you're not just storing the meaning that we've got, like the large language model would do. Here's some text, just store it in your word vectors. No, we can actually store the meaning in the situation that it took place in, so that not only do we have this particular fact, but we have the qualifiers for it. Who said it? Where did they say it? And so as a consequence, systems of the future that are storing in this lossless format will be able to say, yeah, look, I get that. You've got this meaning, but it was said by the New York Times, for example, by a particular writer in the New York Times. You can then say, well, I trust it because of the writer or because of the place that it was in, or not. And so you then have the ability to weigh things that you can't do certainly with a statistical technology that's not considering the whole event. It's only considering the word sequence and the predictability of the next word. What can we get in practice? This is just simple output from the system. It takes fractions of a second to produce it. So here we've got John and Bill wanted to try to promise Beth, Sue, and Samantha to eat the hamburgers, the sloppy Joe, and a BLT. So what does this mean? Well, this means, I'll read it down this way, because there's a function of language called a juncture where you can share these arguments between predicates. So what's happening here is that John and Bill wanted. So we have to recognize John and Bill are a unit of its own. If they want to do something, or if they want to do something, what it means is that whatever want means they want to do whatever comes in the rest of the sentence, and they want to do X. So here, what do they want to do? They want to try to promise. So they want to try. So try is an activity in which John and Bill do something. What do they do? The rest of the sentence. What is the rest of the sentence? Well, it means John and Bill promise. Who do they promise? Beth, Sue, and Samantha. What are they promising? The rest of the sentence. But here you've got what promise means. So it means that they say something. So John and Bill say something to Beth, Sue, and Samantha, which causes John and Bill to become obligated. They're becoming obligated to do, again, the rest of the sentence. So notice that John and Bill want to do something. John and Bill try to do something. John and Bill promise to do something. And then at the end, John and Bill eat the hamburgers, the sloppy Joe, and a BLT. So that, again, is a compound. It has to be worked out as the possible fit. It has been worked out as the possible fit. You could drill down into that too. So fundamentally, this sentence, John and Bill wanting to try, etc., is about promising for John and Bill to eat the hamburgers, the sloppy Joe, and a BLT. It's not for Beth, Sue, and Samantha to do it. So you can demonstrate easily in a LLM. I put a recent example up of it where the LLM gets it wrong because the word promise forces the thing doing the promising to undertake the underlying task. It's not a word sequence probability thing. It's a meaning-based type of thing. The example would be if you promise to eat the fish, then you eat the fish. If you persuade someone to eat the fish, they eat the fish. So those types of things are part of the linguistics theory, which you can't use with large language models. So here, language, let's just summarize what's going on. Large language models are hugely inefficient. Why are they inefficient? Well, they're built on word vectors. They're built on numbers. So if you tell me each word or each token of words in every language are going to be represented by numbers, and the only way that you can manipulate those numbers is by doing a 5-step process in which all of those numbers are, I don't know, added or multiplied, or there's a softmax done, which is a statistical, I think it's statistical normalization. So there's a whole bunch of these steps, and maybe you have to do 1 million of them in order to work out the first couple of words. Well, that's hugely inefficient. And that's the thing driving the need for electricity. It's the thing driving the need for designers that are fixing the problems that are coming out of it. So it's a huge cost of GPUs, of electricity, of data centers, and of time, and that's not good. So the systems can fix limitations, but you're doing all this work, spending all this money, and then you need to build a system to fix it. It's not a good design. The scientific model would be go back and look at your design and work out how you can emulate what the brain does, because at 12 watts, that's a easier, cheaper thing to emulate, and it's better. Confabulations is a problem. Again, that's because it's a statistical knowledge base, not a knowledge base. The fundamental limitation of these large language models is they don't use human-like context. So when you say, how is John, it just recognizes John as the statistical average of every John that it's got from its training set. So potentially millions and millions of times the word John in a similar sentence is used. And as I showed in a recent video, that's a hard thing to get by. It's certainly not human-like. So in the human case, we'd say John, the other person would say, John who? Or what? Who's John? The other challenge is that with a word vector, it's giving you similarity. It's not giving you a definition. So if you were to give a system a word like eat, and it says, well, here's your 2,000 numbers that represent eat, you can't do anything with it. You have to compare it to the LLM itself in order to do all of that stuff, in order to use it for word prediction. I mean, fundamentally, these systems are proprietary. So if you look at how LLMs work, a company releases an LLM that maybe it costs $100 million. They release it and then people start to use it. Well, that's great. But what happens when they release a new version? So if you've got your system, which is just based on this thing crawling through the internet and doing whatever it's doing with its statistical buildup, you can't just replace that if you've got a RAG system and fine-tuning and you've written code to interact with it. Quite potentially, you've got to go and redo all of those subsystems as well that are there to make sure that the main system is working. So that lack of backwards compatibility was the reason IBM was so successful. Back in the 60s, they produced System 360 that gave investment protection by ensuring that all new machines that they released were backwards compatible. So if it ran an instruction in, 1965, it will still run that instruction in 1972. So all of your software is protected, your investment is protected. Let me just move my head out of the way for this deep symbolics example. So deep symbolics are built on pattern theory. So that's a combinatorial system. It's not a computer system. It's not a computational system. And the combinatorial system means that you can simply connect elements up, symbols up, and then use them. And it's extremely efficient. And if you use the atom part of pattern atom, what it forces you to do is only use symbols once. And so that removes the need for search engines and the like. Runs on a laptop. It's backwards compatible. So by simply setting up our languages correctly, you'll be able to use this system across, the system based on the same language, you'll be able to use into perpetuity. And if you build it on lossless meaning, if you fully incorporate context, the good news is that the information you store can be not only reused by everyone if they've got the appropriate access, but you can then reconstruct and make decisions on what they meant when they said something. So lossless meaning offers corporations the chance of storing their knowledge in a knowledge repository of some type, but get full access to it and simply plug it through a language interface in order to use it in a lossless manner. And you can just imagine the benefits to corporations that might have data warehouses storing redundant information. And one of the problems is, how do you just keep track of all of that? So here's another comparison. Let's just start on the deep symbolics model. So here, deep symbolics for language, it basically recognizes the meaning of language. It's tracking the meaning in context and then keeping that context together and storing it losslessly. That's the goal, so that you can use it forever. And by storing things only once, you then get access to that information in all of the places it's used. How does it work? Well, the semantics engine takes text and converts it to meaning. The generation engine takes meaning and converts it to text. So if our examples of the 8 different languages, we show in a small way that this is all possible. This all works. And a pragmatics engine then allows you to enter facts or questions. And when you enter facts, it stores the facts. You enter a question, it checks what you've stored, and it makes sense of it. So that pragmatics engine needs to know what was previously said, and that's what the context engine is doing. So this was the 2017 platform that we used against the Facebook baby environment, where we showed that we could not only get 100% on the tests, but we could also get 100% on the training data that had errors in it. So by simply finding the errors, we could then work out why weren't we getting 100% on the final test. And the reason was because the final test output was wrong because the training set was wrong. So there's great promise in developing this further. And then the discourse engine, if you think about it, when we're talking to each other, you're not just making statements and answering questions. We're also directing people to certain goals. So if I contact, say, a used car salesman and I want to buy a car, I would expect him to ask me the questions that he needs to ask me to find out what sort of car I want. I may not know. I might just say, I want a Lamborghini, and he might say, we don't sell those, but have you thought about, Volkswagen, whatever the one is that I'm talking about. So that's the deep symbolics model. And if we now contrast that in a similar way to the deep learning model, they're based on these word vectors, because word vectors are really compatible with deep learning, and that's, deep learning's been going strongly since about 2012. So after 12 years of really high intensity focus, it's led to these large language models, new data centers, new power generation. And now I think it's a good time to pivot back to, well, what else can we do? So here's the word vectors are compatible, but similarity is not enough. Similarity is kind of okay for certain use cases, but that's not how language works. We need to actually understand the unique differences that people have included in their wording. And there's lots of computation needed. So you're tightly coupling knowledge with language, so it all must work together, which means you need to get that $100 million start with all of that. What was it, 100 centuries or something with a very fast computer, or 100 million years. It takes a long time to do all that computation, and we can save the power and produce better machines by simply using the science behind what I'm talking about. I've often used this example. If you think of a lot of words in a big corpus, a petabyte, I don't know what that is. Let's say there's 10 to the 12 or 10 to the 15 words that we've stored on the internet. That's a lot of combinations. But when you think about how we as humans can use those combinations, 10 to the 3,000, I've done a calculation to get to that number very easily just for one type of sentence. So the actual scale of the permutations that we allow with tremendous accuracy is more like this. And today's systems can never get that much data. So they have to do what they're currently doing, and then, well, they then get those problems. Okay, so what's next? Well, what I'm looking for is support. So share this video. It's a bit longer than normal, but rather than have a future where data centers drives the world economies because everybody's simply selling to these dinosaurs that are simply using this old technology of the artificial neural networks for everything for language. If you pull a language out and we make pattern theory work, then that's just going to save us both a lot of money, improve accuracy, and produce some systems that are just not possible with today's technology. So rather than Stargate, which is the $500 billion project that OpenAI, Oracle, and SoftBank have just announced with support from the US government, rather than that approach, we should focus on the science intently, build on what we've already been able to show through pattern brain theory, which people don't know about in general now, but get my book and you'll know about it. And Roland reference grammar, which is a very thorough look at thousands of the world's languages that's been investigated by a very large number of researchers over 40-something years. So we've got the blueprints now to do the work that's necessary to go into the next generation of language-based AI. So I invite you to join us to go on that journey with Deep Symbolics, which is the branding for the symbolic version of deep learning, which is the statistical approach using artificial neural networks. If people talk about artificial general intelligence, that's genuinely what pattern theory represents. It's looked at how brains work, and it says general intelligence comes from this particular approach, which was shocking to me because, after all, I'm a computer scientist and a mathematician. So to find out that using mathematics in brain theory wasn't going to help me, that was a bit disappointing. But it's also very useful to take pattern theory and take it to the next level to explain things like the evolution of language, the evolution of our bodies, and how our brain was able to develop to do the amazing things that it does. But Peter Voss is, I don't know if I can call him a colleague. I've met Peter a couple of times. I've read his work. He has the definition of artificial general intelligence, which isn't the one that's being used in the mainstream. But if you look at Peter Voss's definition of how to approach AI, I fully support that model. I'm looking forward to talking to him later in this year and sharing thoughts on how we can go forward with AGI, with general artificial intelligence. And as I said, I've used a bunch of references here. So MIT News, the Tom Dietrich article, the Grant Sanderson, really nice videos where he's explaining how deep learning and LLMs work. And Josh Starmer, he did the very complicated one with the diagram anyway, which he makes simple. It's a great video where it's talking about the query, key, and value model that sits inside the large language model. And of course, my book and there the Facebook baby tests where we got the 100% against what were very challenging tests. I think very very good effort from Jan LeCun to go down that path. So there we have it. That's the comparison between large language models and the AI focus in the United States, in particular at the moment, to build massive data centers, to invest in power generation in order to drive those massive data centers, in order to do things for language that aren't going to get us where we want to go because of the errors that are inherent in that system. As Tom Dietrich said, the merging of knowledge with language needs to be split out so that you can have language independently to knowledge, and then you can rely on that knowledge being perfect. So it won't confabulate or hallucinate, as the modern people call it. So thanks again for joining me today. Feel free to ask any questions and online, and share the video. Let's get some movement towards a non-energy intensive AI. Thanks again. See you soon.